Okay, I hope you're able to see my screen.
Yes, sir.
Okay, so this is where we had stopped now. Evaluation of complex line integrals. Okay, today we're going to start a very important theorem that is called as ML inequality. It helps us to actually prove many other very um, uh, useful theorems. Okay, the ML inequality. So we'll have a look at what this ML inequality is, what this inequality is all about. So it provides, as it says over here, it provides an upper limit. Okay, please note here, this is an inequality. Okay, it's not an equality, it's an inequality. Inequality means either greater than equal to or less than equal to, right? So if the inequality it's a less than equal to, that means that's an upper limit. But if we say greater than equal to or simply greater than, then that's a lower limit. Okay, something is greater than something else, then that something else must be the lower limit. Okay, so it provides an upper limit. So here in this inequality, we are going to use a less than symbol. Okay, in this ML inequality. So this ML inequality, it provides an upper limit on what? It provides an upper limit on the estimate. Okay, on the estimate of the absolute value of the complex line integral, of the absolute value of the complex line integral. So what is the absolute value of the complex line integral? The ML inequality provides us a way to find out what is the upper limit, that is what is the maximum value that this complex line integral can take. Okay, so if the ML inequality is applicable on a function, okay, over a certain curve, then that means that function is bounded. It will never take a value which is greater than what is given by the ML inequality. That means it will never become undefined at any point of time on the path. Okay, so let us say C is a curve of finite length. So let's say I have a curve. Let me draw the complex plane here, the imaginary axis, and this is the real axis, and the imaginary axis. Let's say on this curve, there happens to be, sorry, on this plane, there happens to be a curve. Okay, there happens to be a curve like this. Okay, this curve is the curve C. Okay, this is the curve C. Now, this curve C has got a finite length L. Okay, when I say this curve has got it's a curve of finite length L, what I mean is I divide the curve because it's a curve, right? So how do you find out the length of a curve? What you do is you divide the curve into many small parts, many small segments. Okay, you divide the curve into many small segments, and the reason why we divide this into many small segments is inside each segment, within each segment, we can consider the curve to be almost like a straight line. Like for instance, this part here, we can assume that the curve, this is a straight line. Okay, it's almost a straight line. Then you can find out what is the length of this particular segment. The length is, let's say, delta Li. Okay, so if I now do a summation of all these delta Li's, that is, if I add up all these delta Li's, then what will happen is of the curve. Okay, L is the total length of the curve. Is this understood what I mean by this? C is a curve of finite length. Okay, so here L is the length of the curve. L is the length of the curve. Okay, it's a finite curve. L is its length. Next thing, we're talking about another constant. That constant is m. Okay, we said that m is a constant. Okay, we said that m is a constant such that the modulus of the function f, okay, the modulus of the function f at each and every point, that will be less than m. Okay, so when I say function, the moment I say function, that means I have to go to the argon diagram of the range. Okay, so this is the domain, I have to go to the argon diagram of the range. Okay, so we have a real part. This time it's not the real part of z, this is the real part of the function, and this is the imaginary axis of the function. Now, like I said, I showed you the mapping. Let's say this is the point 1 and this is the point 2. Correspondingly, this point 1 may correspond to this point 1. This point 1 may correspond to a point over here. This could be point 1. The value, when you substitute this value of z, the function gives me this value. When you substitute this value, the function gives me, let's say, this value. So as you move along this path C, in the function plane, maybe the curve is going to move like this. In the function plane, maybe the curve moves like this. So you go from 1 to 2 like this. When you are at 1, you are over here in the function plane. When you are here, you are somewhere over here. When you're here like this, and like that you proceed. So you proceed along this curve here. You will find that you are proceeding along this curve in the function plane. Is this understood, this point? Is this point understood? Now, let us say I take samples on this, no? I take samples, okay, on this, each and every one, each and every point, I'll take samples, okay, same as the way I have done over here. Let's say at this point, I have some point Zi, and this Zi corresponds to, let's say, this point, okay, so this point Fzi. Okay. Now what we are saying is, what is this m? M is, I find out the value of the function at this point, this point, this point, this point. Try to find out the value of the function at each and every point on this curve. Okay. And what is this curve coming from? This curve is coming as a result of this curve. When you move along this, you're getting a curve along this, right? So I take any one point, the correspondingly, the function is going to give a value f of zi. So what is this small m? Small m, we say, the value of the function is never greater than, sorry, not small n, capital M. We say that the value of this function, the value that is at each and every point on the curve, if I want to find out what is this, then if I take the magnitude of this, function, okay, you find out the value of the function over here, and then find out the magnitude. Then we say that if the magnitude of the function is less than one constant m, okay, so this constant m is the limit that the magnitude of the function can take anywhere here. So two things that we need to keep in mind. One is the total length of the curve. This is in the complex plane of z. Okay, so total, we have a curve, the total length of the curve is L. And then because I'm having some points here and there is a mapping here, all these points will correspond to these set of points in the function plane. Okay, and you're going from 1 to 2 here means that you're going from 1 to 2 in this direction. Then for each of these points, for any point on this one, we'll have a point on this one. Okay, and this point, what is the value? The value is f of zi. If this is zi, then this point must be f of zi. We find out the absolute value of this and zi. Okay, if the absolute value of zi is less than m for any I, then we say the value of the function is going to be, the absolute value of the function is always less than m. Okay, so we can say that if modulus f of zi is less than m for all I, then, okay, I should not be using the letter I because I means something else here. Let's say use j for all j. If fj is less than m for all j, then we say that the absolute value, or rather we could write it this way, then we say that m is the upper limit, on the absolute value of the function. Is this understood to everyone? Is this understood by everyone?
Yes, sir.
Okay.
Yes, sir.
So here we are taking into account two numbers. One is L. L is in the Z plane. L is the length of the curve, and there is another number which is m. Both of them are real numbers. Okay, both of them are real numbers. M is the max upper limit on the absolute value of the function in the function plane. Okay, both of them are real numbers. Okay, both of them are real numbers. Then the ml inequality, it says that if I integrate over this, if I integrate over this function, if I integrate this function over this curve C, if I integrate this function over this curve C, then that integration value will always be less than this ml. Okay, the integration of over C of this function, if you integrate over this curve, if you integrate this function f of z dz, then this will be always less than m, where m is the upper limit of the function over this curve and l is the length of the curve. Okay, the total length of the curve. So this is known as your ml inequality. Is that understood? Okay, so okay, sorry, I forgot. It has to be the absolute value. The absolute value of this function will always be less than ml, because these are real numbers. I cannot simply put a complex quantity in as less than ml. Okay, not possible. So this is real number. So I have to take the absolute value that is going to make it a real value. Okay, so this is what we have. So this is your ml inequality. Okay. So now suppose a question is asked, okay, find the upper bound for the absolute value of the integral so and so, where c is a straight line between 0 and 1 plus I. So let's do this problem. Okay, so let's say I would like to do this problem. Say we want to find out the upper bound of the absolute value of the integral. Okay, in other words, what they're asking is they're finding the upper bound, that is, find the upper bound for modulus c z square dz. Just 1 second, okay? Just hold on. Also, just give me 2 minutes, okay? I'll be right back. Just a second. Okay, sorry for the interruption. So let's again head back to where we had. Okay, so this was the problem. So we have to find the upper bound of the absolute value of the integral, this one. And C is a straight line between 0 and I1 plus I. Okay, so this is what we are supposed to do. So first things first, let me just draw the coordinate axis, sorry, the complex
Sorry, sir.
plane. Yeah,
Sir, I tried to solve. Sir, is the answer square root of 2?
I think so. Sounds right. That sounds right. That sounds right. Okay.
Okay, sir.
Let me just do it once. Okay. So here we have 2 points, right? So this is we have, sorry. So we have, this is the real axis. And oh yeah, anybody else have you tried to solve? Okay, only Mehul. All right. So we have 2 points. One point is 0. Okay. One point is 0. And the other point is 1 plus I. That means 1 unit along the real axis and 1 unit along the imaginary axis. So this point. Okay. So this is the complex number, that is 1 plus I. Now what we need to do is we consider the path. According to this, the path is the straight line. The path C is the straight line which joins these 2 points. So this is the path C. Okay. So now we need to find out the upper bound. Okay. So by Ml inequality. So here, first of all, we need to figure out what is M. Okay. We need to find out what is M, and we need to find out what is L. Okay, we need to find out what is L. L is very easy. L is simply the length. Length means this particular length. Okay, so length will be simply equal to the modulus. Okay, the modulus of this number 1 plus I, that is 1 square. Sorry. This will be under root the number times its conjugate. So under root 1 plus I 1 minus I. Okay. So which will give us, of course, which will give us 1 square plus 1 square, which is equal to root over 2. So L is root over 2. Now the next thing that we need to do is we need to find out the function. The function is z square. The function is z square. Now this is a monotonically increasing function. So we need to find out where does the function have its maximum value. Okay, where does this? We need to find out where does the modulus of this function take its maximum value. The modulus of this function will take the maximum value wherever the modulus of z is maximum. The modulus of z is maximum at this point on this curve. Okay, this point has got the highest magnitude, so it will have the maximum value here. So that will simply be equal to um, this will be equal to f z at z equal to 1 plus I. Okay, now what is f of z? F of z is z square. Okay, so which is at z equal to 1 plus I. So now we'll obtain this is equal to modulus 1 plus I whole square, which is equal to modulus 1 square plus I square plus twice I. This gives us modulus 1 square is 1, I square is minus 1 plus 2I. These two will get cancelled, and when you take the modulus, this I will go out, so only 2 is going to remain. So that's the value. So this is your M. This is M. Okay, so M is equal to 2. So therefore, by the Ml inequality, okay, by the Ml inequality, therefore, by the Ml inequality, the modulus of the line integral of z square dz over this c, okay, this is what you're supposed to find out, z square dz, this will be less than m into l. M is 2 and l is root over 2. So this is the upper bound. Okay, Mehul, I think this is what you got, no? 2 root 2.
Yes, sir.
Okay, great. So this is how we solve problems like this. Okay, this is a very simple problem. Mainly, we don't use ML inequality for solving problems like this. We use ML inequality for helping us prove some, let's say some theorem. Okay, it help, and we use the ML inequality over there. Okay. Next we have this paths and connectedness. Okay, so I'm going to stop here. Okay, it's 1:40. The reason why I'm stopping is, I mean, today it's a day of like many meetings. Okay, so I have one more meeting to attend. So I'll stop here with at ML inequality. Next class we'll look at